name's Trevor Hildebrand.
I'm Alex Hafner. I'm Dan Heilman.
I'm Chase Morgan.
Aldi Wilson.
I'm 贺阳琪，I'm 尹雪。
And we are soil. So, Institute soil washing, so we can we'll get started. So just to provide a little bit of framework, we'll be coming back to this this figure later on when we talk about field implementation. But this is just to start off to let you know what we're working with. This is in situ soil flushing. In situ soil washing can be used interchangeably. So you can see right here we got the contamination plume with the injecting well and then an extracting well. And then what makes it a washing procedure is this part right here, washing solution. So you can see it looks similar to a pump and treat method, but what we'll show you in the next couple of minutes is the washing solution enhances a traditional pump and treat method. And like I said, we'll come back to it, but then there's some separation and then contaminant treatment afterwards. So yeah, we have an injecting well right here, but just for your benefit to see, another application is spray application. So there's no injecting well. It's just the natural infiltration into the contaminated area, still having the extraction well. Okay. So why soil washing? Like I said, it's also referred to as soil flushing. And this method enhances conventional pump and treat methods by increasing the mobility of contaminants with the injection of an engineered aqueous solution. I said engineered aqueous solution because there are multiple additives that are found to be common to work best. Those include surfactants, alkalis, and co-solvents. There are other additives, but we're just going to cover these because it would take an entire class to go through everything. But these are definitely the most important that you should know for any type of introduction to soil flushing. So like I said, this is an enhanced version of pump and treat. So to start off, we can explain the mechanism of pump and treat is miscibility, or in other words, liquid solubility. So it's basically just solubility when two liquids are concerned. And in our case, our specific case, the liquid solute will be an apple, or an L-NAPL or a D-NAPL, because we were talking about remediation. And then our liquid solvent would be water and pump and treat, but with soil flushing, water plus that additive, that engineered aqueous solution. So two key things to keep in mind. Primary removal is the direct extraction of the contaminant. So like in the extraction well, directly pulling the NAPL from the soil. And then secondary removal, I have it bolded because this is the important part, extraction of contaminant and aqueous solution together. And that's where soil flushing really comes in handy because it has to mobilize the contaminant because primary removal is no longer an option. So miscibility and mobilization of the contaminant. So we're all familiar with this figure, this schematic. We've seen it a lot throughout the semester. And this is what I'm referring to as primary removal. The NAPL is in the continuous phase throughout the strata, the rock strata, and pump and treat can be effective because when you apply a pressure gradient to that, it will be the oil that comes out. But as you know, as that oil depletes and the water saturation increases, secondary removal is the key. Water is then in the continuous phase, and pump and treat is no longer effective because water is being pumped out, not the oil. And then, yeah, there's a transition area too, obviously. So to keep that figure up for reference, we can talk about the principle of mobility. Mobility is permeability over viscosity as it relates to water, in the case of just pump and treat, and mobility of the NAPL, what we're trying to get out. You can see it's a ratio, so if we have a mobility ratio less than 1, that means the effects of, or that means the mobility of the NAPL is greater than the water, which is great. That's what we want. We want to get the NAPL out. But then, like I said before, the mobility of the NAPL is limited as it becomes extracted. Your mobility ratio increases, goes over 1, and you're just getting water out. You need to find a way to get the NAPL out as well. So yeah, soil flushing is thus required. So the mechanism for soil flushing is enhanced miscibility. And there's a couple ways to approach this, a couple ways to explain it. Hopefully this is a simplified version for just this introduction. And we can start to begin to understand the mechanisms and the processes that are involved. So the forces acting on the napple, and just for ease, I'm pretty sure you're familiar with the schematic, just a droplet, or a drop of oil or any type of other liquid organic on a solid surface. The forces acting are the buoyancy or the advective forces, and I kind of lumped advective forces, and you can think of like the flow of like the surrounding aqueous solution, kind of like a shear stress, like coming by, flowing, and then slowly dissolving that napple, and then of course buoyancy because there is a difference in density, and then that's acting to take it off of the solid. But the interfacial tension and the van der Waals forces, electrostatic force, and interfacial tension is keeping it on its side. So we have to find a way to lessen that interfacial tension, because we can consider buoyancy and advective forces to be constant if we keep like the pressure the same with the pump, and then the van der Waals forces we can consider to be constant. So what we can do with our engineered aqueous solutions, we can target that interfacial tension to help us out with miscibility. So for reference, we have Young's equation and the Young-Dupree equation. So to go back to this, we have our aqueous solution, we have our oil, and then we have our solid. So you can see how the interfacial tension between the oil, O, and AQ, the aqueous solid, is inversely related to the contact angle. So if that interfacial tension is decreased, that means the contact angle is going to rise, which you can imagine this as opening up, forming a sphere of water, not lying flat on the surface. So again, just to reiterate, we need to target that interfacial tension. And then the Young-Dupree equation references the work of adhesion, which is the work needed to separate or detach that oil from it. And again, if the interfacial tension, this is the same variable, if that's lessened, the work is also lessened, so it's easier to remove it from the surface. And to go back to the free body diagram, I guess you would say, if this is lessened, this is constant, and this is decreased, your advective forces and your buoyancy are able to dominate, and then you'll have miscibility, you'll have mobility of that napple. So to go back to this, that's just like the mechanisms behind it. So how do we get there? We have surfactants, alkalis, and co-solvents, like I said before, and those are what are used to target that interfacial tension. So to start off, surfactants, they promote solubilization. A surfactant, abbreviated form of surface active agent. We have a hydrophilic head, which means water loving, and then a hydrophobic tail, which means water hating, or it'll dissolve in an oil or hydrocarbon, organic liquid. So for simplification, I use the squigglies for straight lines. So the hydrophobic tail will dissolve in the oil initial solubilization will dissolve, and then the hydrophilic portion will stay out in the bulk liquid. Both will dissolve, and so that action decreases the interfacial tension. And to go back to those equations, when that's decreased, that means the contact angle increases. So this angle opens up, increases into form a droplet. And so that occurs at the critical micelle concentration when there's enough surfactant to surround that oil. And what will happen, it will lift it up and create an emulsion of napple and water. And you can, like you've seen, like when it rains on a parking lot and you see the gas bubbles, or like the gas droplets in a rain puddle or something like that. And then you can imagine how mobile the napple will become. We'll be able to pump it out. Yeah, and the term can be used as solubilization, or sometimes you see it refers to as rolled up, obviously because it's rolled up to a volume and able to be lifted up. Next, alkali addition. So we mentioned saponification because this enhances mobilization pretty much to the same process. The only difference is the surfactant is created in situ. It's not directly a part of the injecting fluid. So saponification, the production of soaps. So soaps are salts. That includes sodium and potassium, and then with an organic acid chain. And then when that's created, it serves as a surfactant, so it serves as one of these. So this will be your salt, and this is your organic acid chain. So when the alkalis are injected, they react with the organic acids within the napple that are already present in the substrate. You're just adding in the salt, and yeah, like I said, they form the surfactant, and this is the reaction that takes place. So organic acid already present in your napple. You have your alkali, sodium hydroxide, potassium hydroxide, among others, and then you create your surfactant. So this is the hydrophilic part, the salt, and then the hydrophobic part, and then water. And so because you're creating a surfactant in situ, that reduces, or that lessens the need for surfactants you actually need to inject, which is good for a couple of reasons. Sometimes the surfactants can absorb onto the rock itself, and then you can't get your surfactant out. So, plus a cost benefit there too. So lastly, for the mechanisms, co-solvents. So this promotes miscibility between the napple and the water. And co-solvents can be alcohols, methanol and ethanol are popular ones, ketones and esters, and they're added to promote miscibility. And the reason for that is because they dissolve both in water and in the oil and in the napple. And then if a sufficiently large amount of that co-solvent is added, a large enough concentration will be present in both phases, and they both will become miscible. So this is from our 408 notes. So in this example, isopropanol is used. It's a co-solvent in alcohol. It's able to be dissolved in both oil and water. And the result is interfacial tension, what we're trying to target from the very beginning. That is lessened, and oil and water are able to be present in the same liquid. And it's modeled to run as a plug flow. So once the alcohol comes in contact with oil and the water, they both will dissolve and can come out all at once. Okay. Somebody else want to?
So yeah, like we kind of discussed earlier, soil flushing is different from soil washing. Soil flushing happens in situ, so the water kind of goes through the soil, whereas soil washing you have to take an excavator, get all the dirt out, go through a whole facility to kind of wash it. Normally the facility's on site, but in situ is still just easier. So to talk about some of the influencing factors of the geology, first is the grain shape and size. So whether it's a clay, silt, soil, how big it is, if it's completely circular or it's kind of odd, like it's more square. That kind of follows into the permeability and the porosity of the soil. So, if you have a bunch of square particles are going to click together easier than circle particles. So you'll have a higher permeability if they're more circular. Any possible fractures that can be in there, whether it's from an old earthquake, even an old well hole, I guess, like maybe 2-3 centimeters in diameter. There's any fractures in the ground, and the hydraulic conductivity. So here we have a graph showing the different regimes of soil washing. So right here you get difficult. This is easier to soil wash, and this is the easiest to soil wash. So if we go way over to this corner, and where my mouse is, you find that the diameter, particle diameter, is very small comparative to the other particle diameters, and you have a high concentration of weight for that small particle. So it's going to be, small particles such as clay. Clay is going to be impermeable, so it's going to be very hard to get water to flow through there. So that'll be up in the fine silt. Another thing I'd like to mention is that this sieve throughput by weight takes into account the liquid, the saturation of it. So now if we go over to the other side, kind of by the gravel, we find it's 100% by weight of the larger particles. It's going to be easier to wash than this, but as the water saturation actually goes the opposite way, so water and napple saturation, as it increases, you're going to go down in the throughput of the gravel size because you're going to have more water. So the more water, the more napple there is, you're going to go farther down this graph, and it'll become easier to wash the soil. Like Trevor was saying, the more water there is, the easier it's going to be to sort through. So here, taken from the 408 notes, you see two particles in contact. This is water / a fluid, and you have two equal-sized solid particles here. So if we go back to the notes and remember the notes, the capillary pressure to get that fluid off of the particle grains is inversely related to the radius. So the larger the radius that they have, it's going to be easier to get all the fluids off. But the smaller radius or the smaller particle size, it's going to have a higher capillary pressure. So you're going to have to put more energy, add in more surfactant to the solution to kind of get it through those smaller pore spaces. Moving on to fractures in the ground. I guess everyone should know this. It's kind of common sense, but if you have water, it's going to want to flow through the fracture before it flows through the porous material. It'll be easier to flow through the fracture. So you kind of have to take into account where the napple penetrated the ground at, where it flowed, what fractures it might have hit, and where it might go, because not all fractures are vertical. So I'm going to kind of go diagonal. So you got to be aware of how far the napple is going to flow. So the top graph, we've seen this tons of times before, but you get to the saturated water down here, up here, sorry. And when you come back down the curve, you can, no matter how much pressure, how much fluid you use, you're still going to get a concentration of the napple stuck in there. So it's very hard to remove all of the napple, all of the contaminant by just washing it. You need something else to kind of make up for that space. Kind of shown, like right there, it's going to stay within the pores, the small contact angles of the fracture. So we're kind of going to weigh the good and the bad geological characteristics from it. So some pros, which would give you a better overall soil flushing experience, would be homogeneous media of the soil and the aquitard. So if you're in a confined aquifer, I guess you're going to have that aquifer on the top and the bottom. So you want to make sure that there's no geological layers that are permeable in that lower aquitard, or else it's kind of going to flow through there, you're going to have to get a larger area to do the soil flushing. Equivalent size particles, and they want to be larger, so the size, you want to have a larger size. And you want to have a large hydraulic conductivity for water to flow. So that's again going back to the kind of particle size, pore space. You want the water needs to flow through there. Some bad geological characteristics that might be had is like a heterogeneous media. So there's soil in there, but it's all the pore space is kind of filled with small sand particles and small silt particles. It's going to be more impermeable than just a homogeneous media of soil. Another con would be the multiple fractures, because if you're going to kind of send water through there from the injection well to the output well, if you have a large fracture in there, the water's kind of gonna go that way, so it's not gonna make it all the way through your system, and there's a whole flaw in your system if you don't take into account the multiple fractures that may be in there. And then again, high concentration of small particles such as clay or silt, so that's gonna get within the pore space and make it more impermeable. Here is just kind of an example of some leaks that you might have. So you have light non-aqueous phase liquid here that sits on top of the water table, and you have a dense napple here that goes all the way down to the aquitard at the bottom, the impermeable layer. So some flaws that might happen, there might be like some fractures in the impermeable layer. That's gonna make it more difficult to kind of wash through the solution, because you're not going to be able to get in there. It depends on whether it's a L maple or a D maple versus how far you put in your recovery well. That's going to take the saturated water out from there. If you have a D maple, you're going to want to put the recovery well lower to get all that versus higher up. But there's just many different characteristics that you have to take from the geology to be sure that you can do this. So then some influencing factors of the NAPL would be the interfacial tension to the soil. Obviously we talked about that. The saturation, the water saturation versus the NAPL saturation. The viscosity and again the density of the NAPL. The amount that's spilled over the area, is it all contained into one drum leaking, or is it through an entire plant where you have drums a few miles away from each other kind of leaking? You have to take that into account. And then the capillary pressure. So yeah, it's dependent on how much intrudes into the aquifer, whether or not, how much water you're going to have to use, how much you're going to have to use anionic, cationic additives. It's all going to change the process, and you kind of have to figure out how much is there, what it is, what concentrations it's in the water. If you have like a dense non-aqueous phase liquid, it's going to sink to the bottom of the water table, but you're going to still have traces of it. And maybe the vadose zone, maybe the upper part of the water table, if its interfacial tension is too high. So you're going to have to take that into account as well, how much may have got trapped on the way down that you have to revisit. Did everything fall, or did most of it kind of get trapped in the plume there? And then here's the different saturation states. So this is fully saturated. It's going to be easy to remove the liquid here. This will be a little harder to remove, and it gets harder as it's in the funicular and pendular saturation. You're going to have a really tough time removing the last percentages of the NAPL in the ground if it's within that those small pore spaces. So you can add the additive that'll kind of decrease the interfacial tension of it. So that's one way that could help you get through the small pore spaces. We got a quick 2-minute video. So yeah, this is in England.
So we're here at a site in the northwest of England. It's a former builder's merchant that has now been demolished and it's been redeveloped into a supermarket. The builder's merchants itself had a series of underground storage tanks on site, and these tanks house diesel so they could fuel their delivery trucks. Over time, these tanks have leaked and have contaminated the underlying groundwater. Regenesis Remediation Services, RRS, are here to undertake a series of in situ chemical oxidation exercises using our product Regenox. One of the rather elements.
So he was talking about his project Regenos. That's their specific like concoction that their company uses that can. It has a different concentration of the cationic, anionic, hydroxides, this and that, and it's going to be different in each remediation site that they encounter. But that's that's one of them that they do. So that's their specific product that they're going to incorporate here.
Relevant solutions with in situ chemical oxidation, when applied through direct push injection, is that it doesn't disrupt the ongoing build program. So as you can see, they're sort of 2 weeks into the earthwork exercise, the cut and fill exercise on site, and we can carry on with the remediation without interrupting the build program.
So that was a big point that he made. All you need is like they're going to go on to say that they have many injection wells here, but I mean, you don't need a lot of space for this to take place. You might need a space for the washing part of the soil, but it's very small. It takes up a very small ground space, so they're still able to do the remediation project while the construction company is building.
What we're actually doing here is we're undertaking a series of injections across a relatively small area, so 20 square meters.
He was just mixing up their solution, so I don't exactly know what that is, but that's their special chemical product additive that will make the diesel fuel its interfacial tension decrease.
We're injecting the Regenox across 10 to 12 points. This will be undertaken during 3 separate campaigns, each lasting about 2 to 3 days. During the final campaign, we'll also be applying another product, ORC Advanced, Oxygen Release Compound Advanced, which will just enhance the aerobic biodegradation of the dissolved phase petroleum hydrocarbons.
So that's just an example of like field implementation.
This picture is provide an illustration of one type of in-situ soil flashing process used in the industry. This process begins with the drilling of the injection well and extraction well into the ground where the contaminant has been found. The number, location, and depth of the injection and extraction well depend on many geological factors, and engineer considerations. So wells may be installed either vertically or horizontally. The soil flushing equipment pumps the flushing solution into the injection well, and the solution passes through this contamination area and picking up contaminants along its way and move towards the extraction well. And the extraction well will pump the outer solution underground. The contaminants are mobilized by solubilization, formation of emulsions, or a chemical reaction with the flushing solutions. After passing through the contamination zone, the contaminant-bearing fluid usually is collected and brought to the surface of the ground for disposal, recirculation, or on-site treatment and reinjection. Traditional flushing techniques rely on the ability to deliver, control the flow, and recover the flushing fluid via a pump and treat system. Because we use a lot of chemical reactants in this washing solution, so in the separator part, we mainly separate the surfactants and flushing from the recovered flushing fluid for reusing the next process. And it's a major factor in the cost of soil flushing. Treatment of the recovered fluid results in sludges and residual solids, such as techniques such as the carbon or the ion exchange resin will be used in this part. And for the next step, the contaminant treatment is mainly the water treatment, because the wastewater used in this process will be contaminated and must be treated. So the techniques like neutralization, carbon treatment, ion exchange, flocculation will be used in this step, and the water will be meet the standards to disposal or reuse. And in the some cases, we need to use the air emission control, because gas like from the volatile contaminants from the recovered flushing fluids should be collected and treated. And the final part is the concentrate residuals. Residual flushing activities in the soil may be a concern and should be evaluated on a site-specific basis. So overall, there are many different soil washing systems that can be used in the industry. Soil washing is often used in conjunction with other techniques because it can use effectively in concentrate the contaminants in the soil. It would be easily treated by other techniques.
So we have an example from Pittman, New Jersey. This is called the Lipari landfill, and I'll give you some background about the site. So originally, in the 1960s and 70s, the landfill operated as a sand and gravel pit. So it was originally engineered to hold toxic chemicals. And the problem is they didn't really have a plan what to do with it after, and they didn't really foresee like what was going to happen. So as you can see, they probably had 3 million gallons of liquid waste and 12,000 cubic yards of solid waste that were disposed of at the site. And the reason why they chose this site to remediate was because in like the 70s, there were actually a lot of fires and explosions that started to happen because of all the volatile organic compounds that were disposed of there. So they started off the project by actually putting that fence around the site in 1982. And so what did they do to clean up the site? So the EPA, they completed a cutoff wall that was underground and a landfill cap because they didn't want water infiltrating the soil and actually flushing a lot of the chemicals down gradient. So they put in a cutoff wall that was completed, I think, 2 years later, and they put on a landfill cap so that no more water could actually come in from, rainwater. And then in 1985, they decided to do the soil washing, and they started off by installing the extraction and injection wells within the landfill. And obviously they put other wells in there to monitor the surrounding area that was like down gradient from the from the landfill. And they just started to pump water in and treat it. So in actually 1990, they did an on-site treatment plant to clean the groundwater that's being extracted from the landfill, and the whole flushing took about 16 years, and it was flushed with clean water, but also was had additives in it to remove the VOCs, and then it was treated on site and sent to a sewage treatment plant afterward. And in 2000, they saw some issues with the project because a lot of the compounds originally evaporated into the subsurface of the ground, and they actually had to remediate that as well and extract that. And that's one of the reasons why they originally put the cap on, because they didn't want those gases leaving either. And now today, the project's over, but they just continuously collect data from the 16 monitoring wells around the area. And they knew it was over because the concentration of the VOCs had lowered to a level that was like EPA standard. So they just stopped pumping. And overall, the treatment was successful from starting at the barriers to the remediation. And yeah, that's about it.
Okay, so for applicability of in situ soil washing, this is just a combination of thoughts that Alex and Trevor have already discussed, but it's nice to organize things together. So it's most effective when used with non-complex soils that have one type of contaminant. It's going to be easier to make the soil washing fluid to treat the contaminants in there. If you have multiple contaminants, then they'll just make it tougher and tougher to find the right contamination, to find the right soil washing fluid. And it's also most effective when used with coarse soils that have a high concentration of sand and gravel. Studies have shown that it's mostly effective with fuel oil and jet fuel. It can also be effective in treating gasoline and diesel fuels, but better options are available for those, like thermal desorption and biodegradation. It has high VOC removal rates without the use of any surfactants, so just the water flushed through the soil there would remove 90 to 99% of the VOCs. The semi-volatile organics, the removal rate is not as high and does require some surfactant addition, but it definitely can be used to remove those in certain cases. And if you have metals or pesticides, you'd add some acids or chelating agents that can bind to those and dissolve those, and so they can be washed with the washing fluid. Some limitations to in situ soil washing. as I said earlier, a complex mixture of contaminants just makes it tougher to make the right soil washing fluid. And it can also be tougher to, sometimes one type of washing fluid would help with one type of contaminant, but it would deteriorate the effects on the other type of contaminant. So you're probably gonna have to just do an ex-situ process for those. And it's not cost effective for a high percentage of plant silts because you're gonna also have to do some type of separation for those types of soils. It is relatively ineffective at treating hydrophobic or insoluble contaminants because the hydrophobic contaminants would not flow with the water that you wash it through. And the insolubles also the same case, they will flow with the soil washing. And it can be difficult for the site conditions that if you have a large area of contamination, it can be difficult to take representative samples of the soil because you need to take those samples before treatment to see what type of contaminants you have and to engineer the right type of wash fluid. So it can be difficult to take representative samples because if you have a large area, as I said, sometimes maybe in one area or one part of the area there will be one type of contaminant and a whole other part there will be another type of contaminant. And sometimes, in some cases, field engineers wouldn't catch that other contaminant and they make that engineer the washing fluid and they wouldn't treat all the contamination. Some other site conditions to consider is availability of water, electricity, and roadway. Of course, you need water to, if you have water available near the site, it will make it easier to get the water needed for the wash fluid. And electricity also helps. You can get mobile generators, but if you have electricity on the site, it will just make it more and more cheap. And in some areas, if it's a really remote area, you're gonna have to build a roadway for the tanks and all the equipment and delivery trucks to get on the site.
So this is some information taken from the 2006 version of the Racer. Two of the main cost drivers for this, as we have talked before, are soil permeability. If you have a lower permeability, the contaminant is going to be more recalcitrant and leading to increased cost. And also the depth of the groundwater table. So if you have a deeper water table, you're going to have a higher cost to drill down deeper, and all the engineering controls that are needed to get down to a lower profile. Obviously, as we've said before, all the other factors that go into play also take into account, like grain size, pore size, if there's fractures involved, that sort of thing. And so there was a study done by Lowe et al., which looked over a range of remedial projects that have been done, kind of averaged out the costs throughout the span of all of them, and found that the costs can range from 1.4 million to 18.56 million per hectare, which is can get a bit pricey depending on the contaminant and all the other factors like we've said. But that can, on a smaller scale, that relates more to about $84 to all the way up to about $800 per meter cubed of soil. So you can imagine it's going to get pricier for more progressive projects. And so for the amount of water involved for this washing process also, and the solutions involved can be anywhere from $6 to $60 per liter of water use. So combining all these costs, you can see where this can start to add up, where you get upwards of a few $1 million per project. So this is some information taken from the EPA from 1993. Basically, that from in-situ soil flushing, about 7 cents to 21 cents per kilogram. It's pretty much going to cost to run on these contaminated soils. And if you have obviously lower hydraulic conductivities, these prices are only going to go up for increased energy that you're going to need to perform on these soils. also a range of $75 to $200 per cubic yard per contaminated material, and depending on the amount of waste that you're going to produce from washing this contaminant, whether it's going to be needed to be transported from an on-site facility or to a wastewater treatment plant, where it can be further processed. And there's an example done from a Superfund site in Palmetto Woods, South Carolina, where they found that it cost around $242 per cubic meter of soil that they were working with, and other maintenance and operating costs of $15 per or $20 per cubic meter for flushing operations. So obviously, engineering controls are going to have an influence on the amount of costs that go into working with these processes.
The following table represents estimated costs to apply soil washing technology and sets of varying size and complexity. There are three parameters in the column. For cost per cubic yard, small set is about $32 for easy one, and $49 for difficult one, and $18 for easy one, and $27 for difficult one in large site. For cost per 1,000 cubic yards, the corresponding cost for small site is twice as much as those for large site. And a more detailed cost estimate table, which includes specific site characteristics and significant cost elements that contributed to the final cost, can be viewed on next slide. Now we can see these detailed tables. There are 4 scenarios in total, like scenario A to D. The definition for small site is 2,500 square feet and 2,000 square feet for large site. The difference between this easy one and difficult one is the soil permeability. For easy one is 0.1 centimeters per second, and for the difficult one is 0.001 centimeters per second. As we can see here, total marked up cost for small site is between 40,000 and 70,000. Total marked up cost for large site is between 100,000 and 150,000. In order to give you guys an intuitive feeling, I compared our data with the group bioreactor, and here is the snapshot from their video. Their total marked up cost for small site here is between 150,000 to 125,000, which is triple as much as our cost for small site. Also, their cost for large site is much higher than ours. We can conclude that in situ soil washing will give us more commercially benefits. The range of estimated costs that have been documented are presented in this figure. Costs can be reported per unit volume of porous medium treated, per unit volume of nipple recovered, and per unit area of site. It should be noted that different methods were used to prepare these cost estimates, so they may not be directly comparable, and it should be noted that all of the estimated were prepared for sites with contamination less than 15 meters below ground surface. For larger sites, the costs of chemicals and residual disposal are significant, making up over 60% of the total cost. And for smaller sites, the produced fluid treatment system may also be a significant cost component. The major cost items included in the cost estimate range for soil washing are summarized in this table. From this table, we can see some fixed cost items like injection and pump installation, and some variable cost items like chemicals and utilities. Other indirect costs such as project management, design and engineering, vendor selection can be further included in the estimate cost range. Costs can also be estimated from some case summary reports with cost information for sites with similar conditions, like the similar size, hydrological condition, and contaminant type and amount. That's it.
Great. Questions from the audience?
Actually, I'm hoping this group, I didn't add my slides to Google Docs.
Okay, well, let's leave that for another time. So
Okay.
let's leave it to the audience.
So can I talk to
We can talk later. Yes, thank you. Questions? Go ahead.
So you guys compared it to soil washing. Specifically, like, is it more used compared to soil washing, or which I guess my question is what's better, I guess, or what's more used, in situ or soil washing?
In terms of like how frequent it's used?
Yeah, frequency.
I'm not really sure in terms of like frequency, but the cost analysis, the bioreactor, that's an example of a ex-situ soil washing. So like the price is almost triple what she said. But like in terms of like actual numbers, like how many sites are using one compared to the other, I'm really not sure.
I think it'll determine on like what the soil is. Like if it's more of a clay or a silt, it's kind of very fine particles. You can take it and remove it and send it to like a washing facility. So soil washing for like small particles, but you know, if it's big particles, soil kind of size, you can just flush it out and do the soil flushing. So it'll probably come down to the geology of the site.
What's normal soil washing? Is that ex situ?
Ex situ.
That's for candy asses. We don't do that stuff.
All right, thank you.
Any other questions? Are you sure?
Generally, how many injection well and extraction well do you need in my site?
I know the video said 10 to 12 injection wells.
Okay.
It'll probably depend on the size of the site. If you have I guess a wider site with the slope is kind of going down, but it's very wide, you're going to need more injection cells along there and recovery wells at the bottom, just because it's wider. If it's kind of smaller, you need less.
Yeah, it'll scale with the area.
Yeah, exactly.
There's also the example of the spray application as well. So that's 0 injection wells, just having the spray application and let the natural infiltration penetrate the contaminant site, but you still obviously need an extraction well. So.
Yep. Thank you. Thought you had to leave early. I guess we finished early. Do you want to repeat the question? I lost
Just
the.
how deep you drill.
How deep?
I mean, hate to be redundant, but like depends on where the contaminant fluid is.
Bottom of the aquifer, probably.
Yeah, bottom of the aquifer, or like was said with the primary removal, where you're just extracting the napple itself, and we're not at the point where we need that additive yet. That could be like really close to the source. So we're talking about like multiple extraction wells. You might have one close to the source that's not as deep as it is further down. And then with that, the amount of additive will be different. You need more on the injection or the extraction well that's like further down.
So like the contamination has more time to travel, maybe?
More time to travel, maybe, but less oil saturated. So there'll be more water presence. It'll be harder to get the napple out. So you'll need more surfactants to extract it. But like I said, if you're closer to the source, you're gonna have more oil. So you might be able to do primary removal just without any additives. But yeah, it depends.
Okay. Any more for anyone? I don't have any questions in particular. I thought you guys did a nice job. I thought especially the initial part was set up nicely and the kind of mechanisms, and that led into the rest of it. The stuff on getting costs is always difficult to do. There's no doubt other people have found as well. But, what were your sources? You used the 408 note some, but also beyond
Yeah,
that?
408.
Did you go back to Grubb and Sitar, the original report that was used for those, or apparently not? No.
Yeah, there's a lot of EPA documents on that.
Cool.
Fluid.
Well, you scored in that, unlike the last 2 years' groups who specifically were told not to do ex situ and did ex situ, you did not. So, well done. Any other questions before we take off? Okay, great. Oh, sorry. All right, thanks. So the others with your desks, with the laptops up, you send your comments. I guess you're writing the comments just like me, right, to send to them? So you send them in. And we will not resume, not on Thursday, but on Tuesday and the following Thursday with the final two groups. Great, thanks so much. Good job.